So let's look at the angles of elevation and depression. And if, for example, we take a worm on the ground and a bird on the wire, then we would say that the angle of elevation of the bird as observed by the worm would be this angle here. And that is the angle between the horizontal line of sight, i.e. Just if the worm was looking straight ahead, and the line up to which the worm looks at the bird. So it's that angle between those two lines. That's the angle of elevation of the bird as observed by the worm, or from this observation point here. Okay? And the other angle we look at then is the angle of depression. And again, if we must always consider the horizontal line of sight of the bird if it was to look straight ahead. But then if it was to turn its attention down towards the worm on the ground and look down at the worm, then that would give us the angle theta d, the angle of depression of the worm as observed by the bird, or the angle of depression of the worm when observed from this position here. And we can see that it doesn't really matter if the bird is on the left and the worm is on the ground on the right, and we have our angle of depression there and our angle of elevation there. It can be the other way around too, where the bird is over on this side and the worm is on this side. And in this case, our angle of elevation is still between the line of sight up to the bird, and the angle of depression is still between the line of sight of the bird down to the worm. And what we can also notice is that because we have two essentially horizontal parallel lines, and you could call this a transversal in between the two parallel lines, that actually we have created alternate angles theta d and theta e, and they're actually equal to each other. So the angle of depression is equal to the angle of elevation, and again here we've the angle of depression and the angle of elevation, alternate angles. A transversal cuts two parallel lines, it creates alternate angles which are equal in size. Now let's take a moment to look at the different methods available to us to find the height of an object like a tree using trigonometric ratios. Well, the first method could be if we're looking to find the height of this tree here, and we take advantage of the fact that it's a sunny day, and with that we'll consider the shadows created and use a similar triangles approach. Okay, so a person could go out into the sun knowing their own height. They could measure their own shadow and basically generate a triangle that considers the angle of the rays of the sun. Okay, and then if they wanted to find the height of a tree, then they could measure the length of the shadow formed by the same sun on the same day at the same angle, and then they could realize that really what they have is two similar triangles. One triangle here, they know the dimensions of two sides. The bigger triangle, they only have the dimension of one side. But they can compare the two triangles using a similar triangles method, where this side corresponds to this side here, and this side down here would correspond to that side. And basically the ratios of the sides would be equal. So this side over its corresponding side, h over 2, would be equal to this side here over its corresponding side, 2.5 over 1.9. So the ratios are the same for similar triangles. So by cross multiplying 2 by 2.5 over 1.9 gives us the height, and that would give us the height of the tree equal to 2.63 meters. A second approach would be to use the trigonometric ratios to find the angle of elevation in the smaller triangle, so the guy measured his shadow, and apply that then to the larger tree triangle. Okay, so if you remember from the last example, the guy or person was 2 meters high, their shadow was 1.9, and this generated an angle of elevation of the sun. Okay, the sun is up here, and that angle of elevation of the sun on any given day is constant everywhere. So at the same time, so we have this angle theta in here, the angle of elevation, and we can use the trig ratio tan of that angle equals the opposite over the adjacent. So that must mean that theta is the tan inverse of 2 over 1.9. So this angle of elevation is 46 degrees. Knowing this, we can apply this then to the larger triangle, the one that concerns itself with the tree, and we can draw the same triangle. We know the length of the shadow, we know the angle of elevation of the sun is 46 degrees, so we can find the height of the tree h by simply saying that the tan of 46 is equal to its opposite over its adjacent. So that must mean that the height of the tree is 2.59 meters. And that value is actually less than the value from the first slide, so there is a difference there in our measurements. So one method is more accurate than the other, and we're going to look at the most accurate method now to find the height of the tree, and that's using a clinometer. So the third method is to use a clino meter to measure the angle of elevation, theta e, I'm going to call it. And the idea is that the clinometer is handheld, and the observer, who knows their own height to be 2 meters, measures and stands away from the object they want to get the height of at a set distance, in this case 2 meters, and they use the clinometer to look at the top of the tree, and that gives them an angle of elevation between the sight line and the line of sight up to the top of the tree, and the clinometer will give them a measured value of, say in this case, 39 degrees. Okay, and they'll have measured their distance from the clinometer to the tree here, 2 meters. So therefore we have a triangle of height x that we're trying to find, 2 meters from where the person stood back, and an angle of 39 degrees, and that would tell us that x is equal to 1.62 meters. So that's actually the difference in height between the person's line of sight and the top of the tree, 1.62. And so therefore the tree height itself must be 1.62 plus this extra 2 meters here. So that means that the tree height is 1.62 plus 2, which is the height of the observer. That's 3.62 meters, and that's the most accurate method to find the height of an object. And there's a fourth way to find the height of any given object, this height AB, and that would be to take two measurements of an angle of elevation. So the first measurement would be here at theta E1, and the second one would be at theta E2, and we would note where we take these observations from, at C and at D, and we'd know the known distance between those two readings. Okay, and how we would set about to find A would be that we know what theta E1 is, so if we take that from 180, we'll find this angle in here, A degrees. Okay, and we can then use, so then we have a triangle ACD, and we can use the sine rule to find this length AC, because we can say that the length AC over its opposite angle, which is theta E2, is equal to the length of x, which we know, over the sine of CAD, which is this angle here. Okay, and knowing that, we can find AC. Okay, because angle A plus angle theta E2 from 180 will give us this angle here. So this is known, this is known, and this is known. So we can find the length of AC. And then when we know the length of AC, we have our triangle ABC. We know our angle of elevation, theta E1. We know the length of AC, so we can just use the trigonometric ratio to find the length of AB. By saying basically that the sine of theta is equal to the opposite AB, that's what we're looking for, over the hypotenuse AC, which we know. So AB, our height, would be equal to sine theta times AC.